Welcome to the 22nd session on operating system and Linux. I'm Manibhushan D'Souza, and in today's class we are going to look at a deadlock avoidance technique. So first we will look at what is deadlock avoidance, and we will see one of the technique that is used to avoid deadlock. Now we have noticed two things in the previous classes. One is either we can prevent a deadlock or you can avoid a deadlock. Okay. In prevention, we do not take an action which can lead to the deadlock state. So prevention guarantees that there won't be any deadlock at all, because we will see to it that one of the condition that is required is not satisfied. At least one of them, one of the condition that is required for deadlock is not satisfied. So we take the precaution and we prevent the deadlock. Whereas when it comes to the deadlock avoidance, we don't take a preventive measure, but we don't try to take a route that can lead to the deadlock. Okay, so it is like if it is raining heavily, so if you don't go out, then you are preventing from getting wet. Okay, that's one way. The other way around is you wanted to go out, okay, but you avoid getting wet. Maybe you take an umbrella and go, or you wear a raincoat and go. So you try to avoid going there. So sometimes what happens is you want to bunk the class. So you know that principal will come from the other direction. So you will go from this direction. So you avoid meeting principal on the way. Sometimes what happens is, instead of principal coming from that way, the principal will also come from this way. Then you end up in trouble. So here you may end up in deadlock, but you try to avoid as much as you can. So deadlock avoidance, what happens is you try to anticipate that if I take the action, if I take the particular step that can lead to a deadlock, that may lead to a deadlock, so you don't take that action. Okay. Now, in order for us to be very sure about, or in order for us to avoid the deadlock, we must have the proper knowledge. So if you don't have the knowledge, then I've already told you. So if you go from that way, you may end up in. So when we talk about the deadlock avoidance, what happens is it requires you to have a prior knowledge of the situation or what is going to come next. If you know that, you can avoid it. So that's the idea. So if you know that something is going to happen in future, you can avoid it. But if you really don't know what is going to happen in future, definitely there is no possible way that you can avoid the happening of something. So in the same way, when we talk about deadlock avoidance, what we are trying to do over here is, if you know how much a particular process is going to request in future, then we can keep those many resources with us. So for example, when the process runs, if I know prior that it's going to require a resource next, then I can keep the resource ready. Or if I can't keep the resource ready, at least if that resource is not available, it is already given to some other process, at least once that process completes, I can take it back and give it to the particular process. So in case of the avoidance, okay, the process will, or the system will check dynamically all the resources and the state of all the allocation that it has done, all the resources that it has given, and it will see to it that the circular weight condition is not satisfied. Okay. Now when we talk about the deadlock avoidance, we need to define something called as a reallocation, resource allocation state. Now, what is the meaning of saying resource allocation state? So, it is the current state. So, you have allocated the resources. So, you know very well when the process starts, you give resources to the process. Now, at present, what is the state of the system? Now, how can you define at present what is the state of a system? You can define the state of a system if you know how many resources are available to you. That is the one thing. So, if you know how many resources are available with you, how many you have allocated, and what will be the maximum request that a process can make, then you can define the state. So, at present, I have 5 resources. I have given 2 resources, and I may get one more request for the same resource. For example, I have 3 pen drives with me. I have already given one pen drive to someone else, and I expect someone to come and ask for one more pen drive. Okay, so uh, how much I have it, how much I have given, and how much the request will come. All these things, okay, these all these if you take a state or all these values will define the state of our system. Okay. Now, when we look at the deadlock avoidance, the system can be either in one of these states. So, based on how you have allocated, how many resources you have given, how many resources you have it, and how many requests are going to come. All the 3 things. Okay. So, like your past, your present, and your future. If you combine them together, you get the state. So, a system will be in one of the 3 states. Either it is in the safe state, or it could be in the unsafe state, or it could be in the deadlock state. Remember, in order for a system to be in deadlock state, if you look at this diagram, you will come to know, in order for a system to be in deadlock state, it must be in unsafe state. So, if it is in unsafe state, it may go to the deadlock state. Does not mean that if the system is there in the unsafe state, it is in the deadlock state. No. If the system may be in the unsafe state, but still it is not in the deadlock state. Okay, so from the unsafe state, it will go to the deadlock state. However, from the safe state, it cannot directly go to the deadlock state. From the safe state, it has to go to the unsafe state first, and then it will reach the deadlock. So, remember that thing. So, let's define what is a safe state, what is unsafe state, and what is a deadlock state. Okay, a state is said to be safe state if system can allocate the resources to each process to the maximum extent in some way, but still it can avoid a deadlock. So, in other words, I can distribute the resources to all the processes, to whatever they demand, I can give them, but still I can't have a deadlock. So, without the deadlock, without creating a deadlock among the processes, I can distribute the resources among all the processes. If that situation arises, then you are in the safe state. What does that mean is I can give the resources, but still I don't have I won't have the deadlock. So, without the deadlock, I will be able to distribute the resources. That means you are safe. So, remember, when you are in trouble, when the system is in a deadlock. So, if you are able to distribute the resources to all the processes, and still there won't be any deadlock, then you are in the safe state. Now, in order for the system to have a in the safe state, there must be a safe sequence. So, what's the meaning of saying safe sequence is the resources must be given in a particular sequence in such a way that the deadlock does not occur. So, if you miss that sequence, then there is a chance that you may end up in the unsafe state. So, what is this safe sequence? So, Safe sequence is the way in which you allocate the resources to the process. So you take one process first, give the resources, or you may take the other process first and give some resources, or you may say that you wait for some time, I will give the resources later, or you wait for some time and I will give you the resources. So it is the order in which the request has to be satisfied. So whenever the processes requires the resources, they will come to the operating system, and the operating system has to decide among them who is going to get the resource first, who is going to get the resource next, and so on and so forth. That sequence is called as safe sequence. So what is the meaning of saying safe sequence? Safe sequence, I have already told you, it is the order in which the requests are satisfied. So we have the process P1, P2, P3, P4, Pn. If this sequence, if you satisfy P1 first, then P2 next, then Pn next. If this is in safe sequence, if you go in this way, if this is in safe sequence, what is the meaning of that? It means if the P1 makes a request, okay, for a resource, you will be able to give the resource. Okay, but that's simple as that. So if the P1 comes to you, if P1 comes first to you, okay, P1 comes to you and say, I want 5 printers, I want a hard disk, I want a pen drive, any resource for that matter. If the P1 comes to you and it asks for the resources, you will be able to satisfy that request without creating a problem. Okay, so then definitely there is no problem. If P2 comes to you and if you are able to satisfy the request, then there is no problem. If P3 comes and if you are able to satisfy, there is no problem. There won't be any deadlock. However, there is one small twist in this. If P1 comes to you and says, I want 2 pen drives, but you don't have the 2 pen drives with you, you have only 1 pen drive, and you have given one other pen drive to somebody else. So what you can do is you can ask the P1 to wait for some time until I get the resource and then give it to you. So P1 comes to the system and asks for the resources, and what happens? The resource is not available. So I can give the resource to the P1. In that case, what I can do, or what the system will do, is it will make the process wait, and once the resources which are held by some other process, so P2, P3, P4, once they release their resources, P1 can be satisfied. So P1 comes to you and makes the request for the resource, but you don't have the resource with you, but some other process will complete their work. Once they complete their work, they will return the resource back to you. So by taking those resources, I can satisfy the request of P1. So either I can either I can say that P1 you go ahead, I will give you all the resources, or I can say P1 you wait for some time, I will get the resource, somebody else has taken that resource, once they return it back I will give you, and you can continue. Remember, in this process there won't be any deadlock. If the P1 is waiting, it won't create a deadlock. That's very important thing. So I am putting the P1 in halt. That does not mean that if I hold the P1 for some time, it's going to create a circular wait. Such a situation won't come. P1 can wait safely. Once I get back the resource, I can satisfy P1. Once P1 completes all its work, I can take all the resources that are given to the P1 and then satisfy somebody else. Okay, same thing. So I take some resources. Once the process completes it, I take their resources and then distribute among the others so that others can complete their work. So this is how the safe sequence goes. So it is the order in which I have to do it. Suppose if I miss the order, then I may end up in a trouble wherein process is waiting, but I made a mistake in allocating the resources. In that case, what may happen is the entire thing may end up in a circular wait, and you may end up in a deadlock altogether. Okay. Now let's come back to the first state. Now what is the safe state? Safe state is in which you can allocate all the resources to each process up to the maximum. in some order, but still you can't have the deadlock. What is unsafe state? Unsafe state is if the system has not followed the safe sequence. I told you what is safe sequence, in the order in which, okay. And then we say that it is in the unsafe state. What is the meaning of that? You did not follow the safe sequence in allocating, so you took it and without bothering you just gave the resource to a wrong person or a wrong process. And now what happens is that process cannot complete and you cannot satisfy others, so everybody will now wait for each another. Okay, so the system did not follow the safe sequence when allocating the resources. Okay, and what happens is if a new request comes, remember you are not in deadlock. As of now, nothing has happened. You made a mistake, that mistake is there, but still everybody is able to continue. But the only problem is if someone else comes and makes a request, if a new request is made for the resource, then that request may lead to the deadlock. So what is happening now? Somebody came to you and asked for the resources, and without bothering you just took the resource and gave it to the process without even knowing which is the safe sequence. What is the meaning of saying safe sequence? Remember, P1 has to be satisfied first, then P2, then P3, then P4. Suddenly if Py comes and says I want the resources, then I cannot give that resource to P5. Why? The safe sequence is once P1 is satisfied, then only follow the P2, then only follow the P3, then only follow the P4. It must be in that order. Hope you get the idea. Safe sequence means the order has to be followed. If somebody comes in middle of the line and jumps in, you say that that's not allowed. This is a sequence. I will give resources to P1 first. Once P1 is completed, I will give the resource to P2. Once that is done, P3. Once that, and so on. So if what has done in the unsafe state, you didn't follow that sequence. You P5 came first. You felt a pity on P5. Okay, this is waiting for some longer time. Let me give some resources. You start giving the resources, and now you violated the safe sequence. Now what happens is nothing, there is no deadlock as such. Everything is working. But if P1 comes to you and asks, okay, I was supposed to be the first person to get the resource, you gave the resource to them, now give me the resource. If the P1 makes a request, make a new request for the resource, then when you try to satisfy P1, you may end up in a deadlock. So unsafe state does not mean that you are in deadlock. You are bound to get a deadlock now. So you are closer to the deadlock. Okay. So I have already told you, not all the unsafe states are deadlock state. However, it may lead to a deadlock. Okay. So remember, as long as the system is in safe, okay, the operating system can avoid the unsafe state. Okay, if it is an unsafe state, that means to say that it cannot avoid the deadlock. Now, when will you end up? Suppose you are in the unsafe state. When will you end up in a deadlock state? You will end up in a deadlock state if one of the process comes and makes a wrong request. Okay, so the behavior of the process can control the unsafe state. Okay, now what is a deadlock state? The last one, which you know very well. If the system has some circular weight, that means nobody can continue in that process. Every process is waiting, and we say you are in the deadlock state. So deadlock means you are in the circular queue, nothing can be done now. You made a terrible mistake, nobody can continue because everybody is waiting for others to complete it and they don't have the resource to complete on their own, and you are in the deadlock state. Let's give a simple example to make it happen. Let's assume that I have 12 magnetic tapes with me, okay, or pen drive with me, let's say, and there are three processes are there, P1, P2 and P0, P1 and P2. Okay, P1, P0 requires 10 tapes. So it says I want 10 tapes to continue. P1 says I want 4 tapes to complete. P2 will come to you and it says 9 tapes are required. Remember, you don't give them all at one shot, because if you give all at one shot, then only one of them will continue. and you may say that okay, I will give 10 tapes to P0. I have maximum, I have 12 here, 10 I will give it to P1 and say that okay, you complete it. I will wait for 1 hour, complete and come back, and I will give you then I will give it to P1, then I will give it to P2. It is not. Remember, if you try to do it, then you will avoid multi-programming. What is the meaning of saying multi-programming? CPU will be quiet because there are no process, only one process is running. So you don't want the waste the resources of the system. You want as many programs as possible or as many processes as possible to execute. You don't want the CPU to be idle. So you have that situation there. So you can't say I will give it all the resources to only one, and I will ask it to complete, then I will call the second one, give all the resources. This way in a sequence you can't do it. Okay, somehow you have to see to it that all the three processes are working. Now what you do is suppose say at the time 0 you gave 5 tape drives to process P0. So process P0 said I want some pen drive or tape. 10 tapes were required. You give 5 to them and say okay, take 5 now, and 5 is enough for you now, as of now, and later when you require more, you come to me, I will give you. I won't give you all the 10 because I have to give the resources to the others also. Others are also there. Then P1 will come to you. So P1 comes and asks you, okay, can you give me the resource? You just give 2 resources to P1 and say that okay, I will give you 2 are pending, you require 4, but I am giving you 2, you come later, I will give you the remaining 2. P2 will come and say I want 9. Somehow you gave 2 to them and convinced P2 that you can continue. Now how many you gave? You had 12 with you. How many you gave? So you gave 9 out of 12. So what is remaining with you is now 3. So this is the situation. You have 10 resource 10. This is the maximum request. So you gave the P0 required 10, and you gave 5 to them, and what is the balance? So what is the remaining? Remaining okay is so how much for P5? 5 is remaining. Okay, let me put it here, or let me put it here only. 5 is remaining, and P2 2 is remaining, and P1 I think P2 is 7 is remaining. What did I do if you didn't get it? Total 10 ways required. Currently I gave 5. What is remaining? I have to give 5 to it so that it can complete it. Total 4 was required. That's the maximum need. You gave 2 to them, and what is remaining? Still you have to give 2 more to complete its work. Remember, it requires 4 to complete its work. It cannot to do it with the 2. Okay. So again you have 9 requested is 9. Maximum request is 9. You gave 2 to them, and remaining is 7. Now is this system, what is left with you? Left with you is 3. With this, can you complete the working? Now remember, you have 3 with them. If you look at 3 with them, if you give 3 all the 3 to P0, it cannot complete it. Why? It cannot complete. It requires 5. If you give 3, it says I need 2 more to complete it. You are giving 3 to me, I want 5. Okay, you come to the P1. What is the remaining with the P1? What's the remaining balance? 2. How much you have? 3. So you give 2 out of this. You give 2 to this. You give 2. Okay, to P1. What is remaining with you now? Remaining with you is 1. So 3 were there. You gave 2 to them. 1 is remaining with you, and you ask P1. You go for the completion. I gave it. So you need 4. 2 already I have given you. Now I am giving you 2 more. 4 you got it. Maximum requirement is 4. I am giving you 4. Now go for the completion. So P1 will go for the completion. Once P1 completes it, what you are going to get? Remember, it will not take home all the resources. It will return back the resource to you. So how many you gave? Initially you gave 2. How many you gave next is 2. If the P1 completes, how much you are going to get back? 2 plus 2, 4. So how much you have now? 1 already was there. If P1 completes it, how much you are going to get? You get equivalent to 5. So 5 you got it. So you got 5 here. Okay. Now you go to P2 here. P2 says if I give 5 to P2, P2 cannot complete because it requires 7. You can't satisfy them. So you go to P0 and say what is remaining. So I gave 5 last time. What is your remaining balance? It says 5. Okay, I'm going to give you 5. So you go and tell P1, P0 that I will give you 5. 5 was balanced. 10 you require 10 maximum. I gave you 5 last time. Now I am giving you 5. Go for the completion. By the way, if you give all the 5, how much is remaining with you? Remaining with you is big 0. Okay, because you gave all the 5, nothing is there with you now, but it's all right. So you give it all the, see, 5 is given here, 5 is already given, 10 require. You say P0, you go for the completion. P0 will go for the completion. Once P0 goes for the completion, what it's going to do? You gave 5 initially, you gave 5. Next, it will return the resource back to you. So how much resource you have now is you have 10 remaining with you. So now remaining is P2. You go to P2 and ask how much you want. I want 7. So you already have 10 with you. So you give 7 to 8. Your balance will be 3. Okay. You ask the P2 complete. P2 will complete it. And how many, once it completes, how many resources you are going to get it. First you gave 2. Then you gave 7. So how much you are going to get? You are going to get 9 back. So add all of them. 9 plus 3 will be 12. Remember, once you complete it, you must get the same number of resources. So that means what is the sequence? How did you completed it? You completed P1 first, then you completed P0, then you completed P2. This is the safe sequence. So if you give in this order, then there won't be any deadlock. So hope you get that idea. So this is what is the deadlock. This is how the things are going. I have just given you the example. Okay. Now what happens if P2 makes one more request for a pen drive? Will it be in safe mode? So let's look at this situation. This is the same situation you have. So same situation, 10 were required. You gave 5, you gave 2, you gave 2 here. What if P2 comes to you and makes a request? Can you just give me, you have 3, no? Can you give me 1? Okay, so remember what is the order in which you are supposed to go? P1, P0, P2. This is the order in we are supposed to go. That's a safe sequence. Remember, this is a safe sequence. But what happened? P1, P2 came to you and said, you anyhow, you have 3, no? What are you going to do with all the 3? Give me 1. So you gave 1 to whom? You gave 1 to P2 because you felt pity on that thing and you gave P2. So what is your balance now? Your balance is 2. Now what happens? Now remember, with 1 P2 cannot complete. Remember what is the balance now? With it, if you give 1 to it, what is the balance? Balance is 8. 9 was there, you gave 1 extra. So no, this is not this one. Let's go here. So you gave, this is your 2, you gave 1. So what is the balance? Balance is you have 6. It requires 6 more to complete. It cannot complete it. You have 2 with you. Can you give 2 here? Can you give 2 here? Yes, you can give 2 here. Is it not? It requires 4 was required. 2 you have already given. You give 2 to this. So how many are there? You give 4. Ask P1 to complete it. So P1 will complete it because it got all the resources. 2 already given, 2 you are giving now it. So how much P1 is going to return? P1 is going to return. So remember you gave all the 2, so there was 0. So P1 will return 4 to you. So take that 4. You have 4 resource now. You cannot give it to P2 because P2 requires 6. You go to P1 and you try to give 4 to P1. You say, okay, take 4. P1 says, I don't want 4, I want 5. With 4 I can't complete. You give me one more, I can complete it. So what's happening now? Even though P1 completed it, P0 cannot complete. Definitely P2 cannot complete. Now the system is unsafe. Why it is unsafe? You cannot, even though you have the resources, you cannot allocate them. And if P1 says no, this was my turn, I was supposed to get it, and if P1 quarrels, then you will end up in a deadlock. So this state is called as unsafe state. Okay, so what happens in the unsafe state? If the system is no longer in a safe state because it made a wrong allocation, okay, it gave the resources in a wrong way. So the next question is, how can you solve this one? You can solve this by using avoidance algorithm. Okay, so avoidance algorithm will see to it that you don't try to give the resources in a wrong way. That is, you don't violate the safe sequence, and see to it that the system is always remains in a safe state. You don't go to the unsafe state. Okay, so how does this particular algorithm works? Initially we assume that the system is in safe state, because remember, when you start the system everything is safe. You have all the resources, you never gave any resources to anyone, and anybody made a request, you nothing is satisfied, so you are in safe state. Whenever a request is granted, so whenever you try to give a resource to the particular process, you try to check whether after giving the resources will it create a unsafe state. If it creates unsafe state, ask it to wait. You wait, because if I give you state, even though your request can be satisfied, I have 10 pieces with me, you are asking for 1 pieces, I can be very generous and I can give it to you, but if I give you now, the entire thing will collapse. So wait, and then grant the resources only if the system, after granting the resources, system still remains in the safe state. Okay, suppose if a process makes a request and if you don't have the resource, so that may also come. So remember, you have 5 pieces, somebody comes and asks you, give me 9 pieces, you don't have the 9 pieces, so only you have 5 pieces. He comes and says, give me 9 pieces, how where can I give? So you can say that you wait, when I get, let others complete it, when they complete it, they will give me back their resources, and then I can satisfy you. Okay, but you notice one very important thing. So what is happening is, see, in the previous case, I just told you, the previous example, P2 came to you and asked for 1 resource. Now if you have to follow a safe sequence, what you are supposed to do, you have to tell the P2 that this is not a safe sequence, I won't give you anything, you wait until P0 completes and P1 completes, and then I will give you. So what happens is, you are simply making the process wait. So if you simply make the process wait, what happens? It's not doing any fruitful thing, and the system utilization lowers. So with the avoidance algorithm, system utilization reduces. Now how can I give the allocation? The next one, how to allocate. Now we follow something called as a resource allocation graph, the one graph that I've already talked about. The same graph is being used, however there is a small twist in this particular graph. One extra edge is added in the ordinary resource graph. So you know, resource allocation graph, so the extra edge that is added is the claim edge. So one new edge has been added. So the claim edge indicates that the process may request for that resources in future. So let's show that here. So you notice that this dashed edges were not there in our resource allocation graph. I've already shown you the resource allocation graph in my previous video, so you can watch them. If you are watching this now, just look at here. So you know that there were already a full line. Now I have a dashed line. What is the meaning of this dashed line is, P1 may request for R2 in future. Now it is not making any request, but after some time it may make a request. The same thing, P2 may make a request for R2 in future. So this dashed line is called as claim edge. It will claim the resources later. Okay, so that's the idea that we have. Let's come back to the place where I have stopped. Okay, so claim edge means there is an edge from Pi to the resource Rj, and what is the meaning of that? It means to say that Pi may make a request for a particular resource Rj in future. Okay, when the P1 makes a request, what will happen is it will convert it to a request edge. You know very well what is a request edge. So in future, if P1 makes a request, suppose if P1 makes a request, now it is not making a request. Suppose it makes a request in future, then you make it as solid line. When it makes a request, it is solid line. Remember, I have told you about the avoidance algorithm. In avoidance algorithm, you have to anticipate what's going to happen in future. So you must know the future, then only you can avoid it. If you don't know the future, how can you avoid it? So you are driving on your vehicle, and if you know that there is a traffic jam, you can avoid it. If you don't know, you will get stuck with the traffic. Okay, traffic jam. So that's the idea. So if you know it, you can avoid it. Don't know, how can you avoid? Okay, so here let's come back to this one. Where is it? I went over. So once it makes the actual request, it is converted into the request edge. Okay, so when the resource is allocated, again when the resource is released, once you give the resource to P1 and P1 uses that resource, and after that it will release the resource. Once it releases the resource, you again make it as a claim edge. Okay, so very important thing is that every process must claim the resources before it starts executing. So that's very important. That I've already told you. Every process must say that I am going to use these many resources. I need 5 pen drives, I need 2 printers, I need 2 disks. Everybody has to tell right at the beginning. Afterwards, it will cannot suddenly wake up and say, no, I wanted this, I didn't tell you last time. Then nothing can be done. So before you start, you tell me what resources you want. That does not mean that I'm going to give you all the resources. I will give you what is required as of now, but you have to tell me what is the maximum request you are going to make. So every process will come and say that I want these many, maximum is this. Okay, so the resources must be claimed a priori before starting it. Suppose a process Pi request for Rj, then can you give that request? So that is the next thing. Remember, what is the avoidance? Somebody comes to you, can you give me one resource? So if you are very generous, you simply come and give, take and give. Now if you try to give that, you may end up in a deadlock. So what you must do, whenever somebody makes a claims makes a request for a resource, can you grant that resource? If yes, on what basis are you going to grant? So in this resource allocation graph, you cannot grant the request if it is going to create a cycle. So after you give the request, okay, if it creates a cycle, then that cannot be granted. So grant only if you convert the request edge to assignment edge. Remember, when first the request will come, that will be the request edge. When you grant it, that is going to get converted into the assignment edge. So if you are getting confused, see, initially if you look at this one, so P2 is making a request. Okay, P2 is making a request. So what is this dashed one? That is claim edge. P2 will make a request. In future, P2 is going to make a request. Now the time has come when the P2 came to you and made a request. I want that. So this is a request edge. Suppose if you grant this one, what's going to happen? The edge will change. Now what is the meaning of this? In the previous, P2 is making a request for R2. What is this one? P2 is allotted the request R2. So request has been allotted to P2 and P1 is still going to make the request. It has not made a request. It may make a request. So this is may. Okay, so that is claim edge. Hope you get that one. Okay. So once you convert it, if you get the cycle, then don't give the request. Okay. If there is no cycle exists in the allocation, that means the system is safe. If the cycle is found, then this the entire system may be in an unsafe state. Okay. Then in that case you may have to say to the process which is requesting, now I can't give you. If I try to give you, I will end up in a unsafe state, so you please wait, I will give it to someone else, let them complete it. You go and have a cup of coffee and come, relax. Once I get the other resources, once my resource allocation graph does not create a cycle, I can give you the resource. Let's look at this particular diagram. So how does the resource allocation graph really works? So now what I have here is a very important part over here, and that is R1 is already allotted to P1 and P2 is making a request for R1. In future, P1 may make a request, it is not yet made the request. In future, it may make a request to R2. In future, P2 may make a request to R2. Suppose if P2 comes first and asks you for the resource. Okay, give me the, can you give? It has made a request. What is this one? It is going to claim. It has not yet claimed. Remember, it's going to make a request in future, but no request has been made as of now. What does the the line indicates over here? Line indicates that this is a dashed line. Dashed means claim. This means request edge. What is the meaning of saying requested? It has come to you and it is making a request. Give me R2. So what you notice here? Okay, P2 is already waiting for R1. Okay, you have not given. At least you may feel that you may feel pity on P2 and you may say that okay, now it is making a request for R2. Nobody has made. P2 P1 may come and make a request. So in that it's in future, but it is not yet made anything. It is waiting for R1 and it's also waiting for R2. Let me at least, R1 is already given to P1. Let me at least give R2 to this. So if you give R2 to this, what will happen? This request will be changed to the assignment. So it is already assigned. Now in this case, what you notice? In this case, you will notice that there is a cycle. Now if you are, if you feel pretty on P2 and if you start giving a resource, you will end up in a unsafe state. Okay. So this is what you are, what is written as such. Okay. Now, how can we solve this problem? This problem can be solved algorithmically by using Banker's algorithm. We will look at that Banker's algorithm in future. That is in our next class. Thank you for your interest and we will meet again in our next class.